Hello, good morning, good afternoon, everyone. Today we are here to talk about causality in transversal studies. Today we are receiving Professor Vithor Rosa Franco from Brazil. He's an assistant professor in the graduate program in psychology at University of San Francisco. He holds a PhD in psychometrics with a broad period in Umeå University in Sweden and a master's degree in social psychology from the graduate program in social work and organizational psychology at the University of Brasilia. His line of research, his experience is in social design making, Bayesian influence modeling, psychometrics, behavior economics, and econometrics and machine learning. Today, he will present us about why we fear causality and how to stop it. So, welcome, Professor Vito.
Hi, Ariella. Thank you for the introduction. Can I start?
Yeah, so before we start, to people, everyone, if you have any comments, any questions, please let us know in the comments. And by the end of the presentation, we will have a time so Professor Vito can answer all your questions.
Sure. So thank you very much, Ariella. Um, so I did this presentation thinking, well, we all been there, right? We all work with psychology. We know that everything correlates with everything. And we also know that, of course, it's difficult to talk about cause and effect relation. And But our research is about theories, right? Theories about human cognition or even animal cognition, human behavior, animal behavior, or groups of individuals and how they relate to each other and all of that. And we want to say why people do what they do, right? But we have an impediment. We have a big problem, a big issue that we all have heard before, that correlation does not imply causation. So, of course, this almost a mantra is correct. Correlation does not imply causation. There is no magic around it. There is no way to prevent this. And we know this is true because we all have seen those websites showing like how drownings are correlated to the movies Nicolas Cage does, or how global warming is decreasing piracy in the world and all of that. And of course, these are always spurious correlations. They do not imply that we should stop watching Nicolas Cage movies or that we should keep warming the globe because piracy is bad or anything like that. But this is also an issue, right? Because we are afraid of talking about cause and effect in our research. Or at least we try to talk about it using different words. So, for example, instead of saying that a variable causes the other, we say that it affects, or it has an effect, or it influences, or we try to use these synonyms that don't say explicitly cause, but they mean that we are talking about the cause and effect relation, right? And there is also a problem when we think about our theories, especially in psychology, right? Because a theory says that people that are more intelligent, for example, will have a better work performance or a better academic performance or whatnot, or that people high in extroversion will be more also successful in academic performance, or will also have more friends and it has a uh, protective or protection against um, uh, being alone and feelings of solitude and whatnot. So our theories talk about cause and effect, but our data, in principle at least, and I want to tell you that sometimes maybe they only talk about correlations, right? We cannot derive anything related to cause and effect. But before we can progress in this discussion and before we can talk about some possible solutions, I believe we need a clear definition of what do we mean by causation. What does it mean to say that a variable is a cause of another variable? Okay, so I'm using here, of course, the references I know, the references I like. Of course, there are several hundreds of even thousands of references talking about this topic. But I like to go back to the basics, I would say. And I think a very basic reference would be John Stuart Mill. John Stuart Mill proposed three conditions that are necessary to talk about cause and effect. These, I believe, are pretty well known. They are commonly taught in methods classes, and they are usually present in methods textbooks. And the first condition would be covariance. So, in spite of the fact that correlation does not imply causation, you need to have correlation to say that you have a cause and effect type of relation. So, covariance is important. You need to have covariance to say that you have causation. The second condition is temporal sequence. So, of course, a cause always have to come before an effect. And this is so well established that we have the spook effect at distance or something like that in physics, right? And it's spook because it breaks the idea of temporal sequence and locality and some other principles in science. And the last one is the absence of confounders. So a confounder, it's a common cause for what would we call the independent variable and the dependent variable that we have not observed or measured. Okay. So according to John Stuart Mill, if we can establish these three conditions, we can then say, oh, okay, this type of relation I am observing is a cause and effect type of relation, not just a correlation, right? And when we think about the perspective like of statistics, when we do the calculations per se, always correlation, right? There is also some nerdy jokes saying, oh, always regression. Like ANOVA can be framed as regression, t-test can be framed as regression, factor analysis can be framed as regression, everything can be framed as regression. And regression, of course, can be framed as correlation. So when we talk about methods and analysis, what we are doing is calculating correlations or covariances or dependence between the variables. So the matter of temporal sequence and absence of confounders is a matter of method and design of your research, right? You cannot control this, or at least it's very difficult to control for this when we think about only statistical procedures, right? And with this in mind, we also have Charles Sanders Peirce. And if you don't know Charles, I believe many people haven't heard of him ever, but he's very important for almost everything we do in science. Every time I go deep in the philosophical basis or the technical methodological basis for something we do, I end up getting to Charles' publications and books and ideas. Okay, so he published these two books, Illustrations of the Logic of Science and A Theory of Probable Inference, and basically summarizing roughly what he says in both books. He's discussing the ideas of how we can make a inference, right? A causal inference from our data. And of course, he has some other philosophical propositions for the philosophy of science. So please read this book and you see where many of the ideas we have now come from. But the important point for us here is the idea of random assignment. So in this book, and as far as I know, at least, Charles was the first to present the idea of random assignment in experiments and say that this is the best way to ensure that groups are homogeneous, right? So from these publications that we started with the idea that you need experiment to talk about cause and effects, and then to be able to say that your inference is correct, okay? And apart from this, of course, many others came after. Charles maybe gave some clear representations of this idea, but from this point on, experiments began to be okay. This is the way of doing science. This is the way of talking about cause and effect. This is the best possible methodological approach for doing science. And maybe this also needs some clarification that when we are talking about doing experiments, we are talking, of course, about controlling the variables. So we try to avoid the effects of too many covariates. We standardize the stimuli or the context, the situation for all the respondents and whatnot. But the most important aspect of an experiment is the random assignment to the groups. Okay, so assignment is basically you have a control group, you have the experimental group, the manipulation group, whatever. You throw a coin, and then the coin determines to what group people are being allocated to. Okay, so this is very important because it basically what this is doing is you guarantee that the independent variable does not depend on the confounder, right? So with this, you can guarantee that you don't have anything affecting your independent variable that could also be affecting the dependent variable and making the covariance show up. Okay, so the idea is basically you do random assignment. This excludes the effect of confounders, and if you find a covariance with the design you did where the independent variable is affected before you measure your dependent variable, you can also guarantee the temporal sequence, right? So doing an experiment, it's very important, of course, but what it does exactly is by random assignment, you eliminate the effect of confounders. So of course, from that, you can do a causal inference. So probably we all know that. We all have heard of that. That is probably okay for everyone. But I think we need a better language or better formal language as we are talking about science and we are talking about precision and objectivity, at least to some degree. And like I shown you here, like the book from Charles is from uh, the 19th century. And almost 100 years after that, we had some people talking about probabilistic causation. Okay. And of course, there's a lot to talk about this. I don't want to make a presentation only about this. I want to try to do some more steps. But it's basically summarized in the do calculus approach. Okay. It was proposed by the computer scientist and philosopher Judea Pearl. Uh, all the ideas summarizing, not but explaining what the calculus is in Judea's book Causality. Okay, it's very mathy, so you have to be prepared to see a lot of formulas and all of that. And I myself, I like formulas very much, so I brought it here. And I think this formula is the summarization of the do calculus approach. And basically, if we understand this formula well, everything else is kind of intuitive. Okay. So I have the English translation for this formula, of course. Oops, sorry. I had some issues here. So the probability of an effect is higher in the presence of a manipulated, meaning a randomly assigned cause, than in the absence of the same manipulated cause. So it's just a mathematical representation of what we were discussing before, right? But the important thing of putting a formula like this is that this formula is the representation of what we call in statistics the conditional probability, right? So P, parentheses, the name of a variable, the straight line, the name of the second variable, means that the probability of the first variable is conditional to whatever is the value of the second variable. So what we are saying here is simply that the probability of the effect should be more likely when we randomly assign a specific cause. Say you are studying depression symptoms. So this would mean that you expect depression symptoms um, or the absence of depression symptoms to be higher when you start giving the person some type of treatment than when you are not giving that person any type of treatment. But this treatment has to be randomly assigned. That's why we have that small do before the cause, because it makes explicit the idea that you're doing some experimental manipulation, that you're um, methodologically affecting the probabilities. We are not just measuring those probabilities. But of course, looking at formulas for most people, I believe it's boring even, but it's sometimes too difficult. As I said, like Judea Pearl's book, Causality, it's very mathy. It's difficult to read. You have to have some like good mathematical background and statistics background to understand some of the formulas and ideas. But the beautiful thing about all of this is that this formula has a more efficient way to be presented, or a way that you do not have to have a training on math, or at least not much training of math. Okay. And another important aspect of this formula, and why it's very important to understanding causality, is that it's related to the three conditions we talked before, proposed by John Stuart Mill on how do you say that you have a cause and effect type of relation. So this formula, some people do not agree with this, but in general, we can say that this formula is a mathematical representation of the conditions proposed by John Stuart Mill. Okay, and when we have math, and the important thing and what of doing this is when you put things in a formula, you can manipulate formulas, right? Manipulating ideas and words is difficult, like me talking in English here, which is not my first language, of course. It's more difficult, right? But if we have a formula, it's objective, it's standardized. When you study how to read the formulas, everyone reads it the same. Uh, and we can stop playing around with the formulas and see what happens when we manipulate them, right? But these formulas in particular, they have an even better consequence, that they are related to graphs. So a graph is a mathematical object, is a set, actually, if we want to be formal, defined by nodes, which are simply the representation of the variables under consideration. And I've put here the graphical representation of those nodes. They are usually just these circles with a letter or the name of the variable within it. And then we have the edges, which in this case are the direction of possible causal relations. So I have here possible in italic to emphasize that we are talking about assumptions, right? We are talking about theories. We are not talking about data yet. We are talking about how we think a theory works, or how do we think that variables are related in causal terms, okay? So graphs are very powerful because this graph here is related to a specific formula. So if we play around with the graph, we are also playing around with the formula. And if we are playing around with the formula, we are playing around with the conditions discussed by John Stuart Mill on cause and effects, right? So it's, for me at least, it's very interesting to understand that this helps us understand more clearly what are the necessary conditions to conclude that a cause and effect relation exists. Um, because now I have a very easy tool to play around with cause and effects, so I don't have to think about very abstract concepts of confounders and longitudinal types of relations. I have a graph and graphs that are very easy to read and look at them and, oh, okay, I look at this graph and I see that A is the possible cause of B is the possible cause of C, and A is also the possible cause of C, right? And what does this mean is that we can start playing with the what if question, right? So what if A actually does not cause B? What if B causes A? What type of consequence would I have in the data? Or what if actually A and B are not directly related, but they share a common cause? What would happen to the type of correlations that I would observe in my data? So this is very powerful tool. It helps us understand very complex relations very quickly. And I think most importantly is if you're doing your own research, it helps you to play around with your ideas, right? To what will be the consequences? What hypothesis can I derive from this type of causal relation? So just to give a quick example, like imagine we are doing some research about shark attacks. We go to the beach, and then there we measure how many ice creams every individual are taking. And then we put this data in R, preferably, and we see that ice cream taking is correlated with shark attacks. And of course, this is just a correlation. We cannot come to the conclusion that we should stop taking ice cream so we are not attacked by sharks. And even more weird would say, well, we should stop shark attacks if we want to decrease ice cream intake, right? It is most likely that the climate is related to both, right? When it's warmer, more people go to the beach, then more people will take ice cream, and of course, you increase the likelihood of someone being attacked by a shark. It's probably that simple. But what if we randomly assign ice cream to everyone on the beach? So we say, okay, I have a lot of money. I'll go to the beach and start giving ice cream randomly to some people, right? Some people will take the ice cream and some people will not be allowed to have ice cream, right? So when we do this, when we do our random assignment, what we are doing is we are removing the effect of the climate on ice cream intake. So from that, if we do not observe a correlation between ice cream intaking and shark attacks, we can conclude that, well, so yeah, getting ice cream has no relation to shark attacks. But if we do observe a correlation, we can be sure that, well, taking ice cream is a problem. We should stop taking ice cream, at least on the beach, right? Um, so this is a graphical representation of the idea we were discussing before, right? And you see it's way easier to understand what random assignment is doing now. It's removing this edge. It's removing this arrow, we can say also, okay? So random assignment removes arrows from causes or possible causes to what would be effects. But if we are studying the relation between these effects here, if a correlation pops up, we know it's not because any possible common cause between our variables of interest, right? But this is the question we wanted to get to. What do we do when we cannot do experiments? Because of course, if you are working with psychology or any behavioral sciences or cognitive sciences, this is probably the case most of the time, right? And I want to be very clear that there is no magic. I said this before. We cannot be 100% sure that there is a cause and effect relation if we are using only a correlational or observational study. Okay, but yes, we can do some things. We can do some causal inferences, or at least formulate some hypotheses derived from data that in future studies, or if you're like doing psychological assessment and you want to do an intervention plan or whatnot, you can use these types of insights to have a more informed type of conclusion. So say that we have these three types of real underlying processes here. Okay, so in the first one at the top we have z, the variable z is a common cause for both variables x and y. On the second graph, we have y is a cause of z, which is a cause of x. And on the bottom graph, we have x and y are the causes of z, and there is no type of relation between x or y. Okay, they are completely independent. From these types of causal relations, we would expect or we would observe some types of correlations. Okay, so we can see that for the first and second graph, all the variables would be correlated. So every undirected edge would be present. But for the last graph, we have that x and y, the correlation would be non-significant, but both variables would be significant to z. And we can even complement this result by showing what would happen to the partial correlations. So again, if we are talking about graphs 1 and 2, what would happen is that x and y are not correlated when we condition on z. But for the last graph, we have that the partial correlations would be all different from 0. So these consequences here that what we would observe in the data, of course, and this is considering that you have a large enough sample to identify the effects of interest, that your measure is not too noisy, and all of this, of course, right? All the good practices in observational studies. But this last type of structure is very important for us because when we think about three variables, when we have this type of structures with two unrelated causes for the same effect, this is the key for start making some causal inferences from correlational data. So this type of structure is what we call V structures. Okay, so it's not for a Vithor, I wish, but it's for, of course, the graph, the disposition of the variables in the graph. And the idea is that these structures, they help us reveal signs of causal relationships in correlational data, right? Because again, when we have only three variables, and if x and y are not correlated, but they are correlated to z, the only causal structure that can cause this type of correlational pattern is the V structure, okay? But of course, this is based on a series of assumptions. So we have to be very careful here because these assumptions are central to what we can conclude or if we can do any type of causal inference from correlational data, okay? So we are assuming here that there is no feedback loops, meaning that you have a cause that is the effect of a cause, which is the effect of the cause and whatnot, right? Like when you have depression, this leads to social isolation, and social isolation leads to depression and so forth. So we're assuming this type of things were not present. Um, that the correlation types we observe, they are consistent with the data, meaning, for example, that the lack of correlation between X and Y, it's not due to some suppression effect, but it's a true absence of correlation. And I put this in italic. The last assumption is that all important variables have been measured. So of course, this is a very strong assumption, especially when we are talking about psychology, right? Because we are assuming there are no confounders. That we said it's one of the important conditions for inferring causality, right? But here we have a very uh, distinguished type of absence of confounders, right? Because X and Y are not correlated. So if they are not correlated, and if this lack of correlation is not due to suppression effect, then what we are talking about is that there is no confounder between, in this example, between X and Z and Y and Z. So basically, we're saying, okay, these correlations here do not have another common cause, right? Because if we had a common cause between Z and X or between Z and Y, this arrow here would actually come from those confounders. But see that now we can start playing with hypotheses and we can start playing with a theory, because we could arrive to a V structure that makes sense theoretically from a correlational data, but then one could say, wait a minute. Actually, maybe we could have some confounder between Z and X, for example. And this confounder could be this variable here. So this helps us play around with the idea and start to exploring more systematically what confounders should we explore, right? Because if you're doing correlational research, especially in psychology, probably you are applying a scale or a questionnaire, which probably has a lot of questions. And of course, if you want to have the complete picture, you need a lot of questionnaires, and almost nobody has time to answer all the questionnaires we want them to answer, right? So we always have to cut items or to cut scales in questionnaires. And these, of course, reduce all the variables we can measure at the same time. So having a graph and knowing about these structures, we can start, oh, okay, next time I do not need to measure this variable here. I can measure only, maybe try to identify a common cause between Z and X. Or the next study, I just want to find a possible common cause between Z and Y. So the graphs and the V structure are helping us to make some inferences, to come to some conclusions, and to think about the future, right? What are my next steps to be sure this type of causal relation here is actually true? And I wanted to bring some examples here. So sometimes it's too abstract, even if I'm giving some examples, we can try to think about a very realistic example. So say that you're studying the relationship between sleep quality and academic performance. Sleep quality is variable A and academic performance is B. So, and say that we are doing our research and we observe that these two variables seem uncorrelated in their data. Say that we also measure test anxiety, and we find that both sleep quality and academic performance are related to test anxiety, right? So if we do this, if this is the type of data we have, from that assumptions we had before, we can conclude that, oh, okay, so from those assumptions and from these correlation patterns, it's reasonable to conclude that A and B are causes for C. Sleep quality and academic performance would affect test anxiety. This is a reasonable inference from the assumptions and from the data, okay? And I looked up the literature to bring this example, so it's an example that if we have someone studying these topics here, they will say, oh, okay, it makes some sense, right? Okay, but what we do then? So to evaluate this causal hypothesis, of course, we cannot do this in in a single study, because yes, correlation does not imply causation. So we just derive the causal hypothesis from our data, or a causal inference with some caveats, right? But well, in the follow-up study, now I have some clearer ideas of what I could do, right? So, well, maybe now I have some evidence at least to say that I should do an experiment controlling sleep quality. I don't know if this is ethical or if this would be possible, but anyhow, we could have an experiment that I bring someone to my lab, or I give them some type of um, tool or gadget they can use during sleep time, and half of my randomly assigned participants will sleep as usual, good as usual, and the other half will be receive like small shocks or whatever, so I can interrupt their sleep. And if I observe again a relation between sleep quality and test anxiety, I can conclude that indeed that causal relation is in that direction. Okay. But if I can't do an experiment, maybe I could do a longitudinal study designed to assess whether fluctuations in sleep and performance lead to fluctuations in anxiety. The idea here is not just to look for the correlations, right? But to see, well, if my performance improved from a specific time point to another, what happened to test anxiety? Did it fluctuate? Did it change somehow? And of course, here the matter is more complex because we can think about trait and state, right? This is something we are always thinking in psychology. If the variable we are measuring is constant over an individual's lifespan, or if it changes depending on the situation. And of course, the example I was saying before, we can start thinking about finding some possible confounders between A and C or B and C. And in a follow-ups correlational study, we can test if they indeed lead to different interpretations, right? So say that like the quality of relationships affect sleep quality and also test anxiety, right? Your relationship with, you say, the teacher or the lecturer affects sleep quality and test anxiety. Or even better, like the trait anxiety affects sleep quality and test anxiety. So we could do a second study, and if this was correct, what we would observe in a graph would be that we would have an arrow going from uh, trait anxiety to sleep quality. We would have no arrow going from A to C. We would have an arrow going to from trait anxiety to test anxiety, and the arrow we have between B and C would have to stay the same. Okay, so this is nice because we already know what graph we should observe without doing any research, just knowing what type of correlations of or lack of correlations we should observe. Okay. But I also wanted to bring some like practical example for psychological assessment. So of course, this is ITC. Probably we have someone watching that does not work with research directly, right? So imagine you're doing the psychological assessment of a client, and this client has like an average intelligence, but a low intellectual self-concept. And for the sake of the example, let us assume that according to the literature, these two characteristics tend to be uncorrelated. Okay. During the assessment, say that you also observe that your client has low curiosity, defined as one of the facets of the openness dimensional of the personality, of course, Big Five model. And again, for the sake of the example, assume that prior research indicates that curiosity correlates positively with both intelligence and intellectual self-concept. And actually, I want to bring one question, one matter here, that this time I put the for the sake of example, because I couldn't find like studies indicating that intelligence and low intellectual self-concept is uncorrelated systematically. I found some studies showing some small correlation, some studies showing no correlation. uh, I'm treading to the safer direction and say they are not correlated, okay? But what I wanted to say here is that maybe we have to change how we do research in psychology. uh, we are always thinking about, well, convergent validity, what correlates to what, and we do not think a lot about discriminate, I don't remember the term in English, validity, right? Or what my measure shouldn't be correlated with. And for those who are more like data savvy, maybe you can you probably notice this, that the V structure depends on the lack of correlation. So not having a significant correlation in our study is good if you want to talk about causality and if you want to make some type of causal inference from observational studies, right? But continuing with our example, recognizing this collider structure, it would lead us to an exploratory rather than descriptive profile. Okay, so a descriptive profile would say, oh, okay, this client here is average, has average intelligence, low intellectual self-concept, and low curiosity, and that's it. But if we find this collider structure, if the literature supports the idea of this collider structure, then we could conclude something like, oh, the client's intellectual confidence and cognitive ability affect the curiosity. And with this, of course, we can start proposing target interventions. So when you're doing the assessment, you not only will say, oh, the scores are high or low, but you say, according to literature, I find this type of V structure, and with this V structure, it would be reasonable, for example, to do um, some intervention regarding intellectual self-concept, so you can amplify curiosity. For example, if this your objective, right? You could also do some cross-sectional validation, for example. So you would use different standardized measures. And here is maybe even counterintuitive, right? Because if A and B are not correlated, if the in the first measure we had low average A and low B, we shouldn't necessarily find this exactly same pattern if we do another standardized measure. Okay, so this is probably a bit counterintuitive, because of course we have convergent validity, right? So if A is measuring intelligence, a second measure of intelligence should be correlated with A. But of course the correlation is not perfect, right? So we have some variation between those, and these variations between the tests should not between tests of intelligence and intellectual self-concept should not be correlated to. So this is the idea here. Yeah, we could do other things, but the idea is, okay, I have an idea of the causal structure and I can play around with this causal structure to think of interventions or actions I could do. And of course, with this, I should say again that the world is more complex. I'm showing you just three variables with a good set of assumptions that help us make some conclusions. And what we do with this is actually there is a set of methods called causal discovery. And I hate this name actually, because it implies that we are discovering causes, right? We are, oh, I can do perfect causal inference from the correlational data. I would say it's causal hypothesis discovery, because from a set of assumptions, we then derive some causal hypotheses from data. And of course, if these assumptions are justifiable for your context, okay, the approach is certainly worth pursuing. Of course, the hypothesis will make sense. Not 100% of the individuals will agree, but we have a good starting point, right? So say we have this type of correlational pattern here. How can I derive a causal hypothesis from this? It's a lot of correlations. There are some lack of correlations here too. And actually, there are many causal discovery methods, okay? But I wanted to talk very quickly about three of them. So the PC algorithm is the most traditional one, is the one that uses V structures. Basically, what it does is it looks for V structures, and it depends on correlation, and of course, it will depend on the assumptions of correlation like linearity and normality and all of that. So if I apply the PC algorithm for that correlational pattern, I will reach, for example, this causal hypothesis here. And you can see it's very complex. I have like 30 variables, if I remember correctly. So it's not possible to explain this graph with words only. But looking at the graph, you already know, right? For example, you see that variable 29 and variable 28 are the possible causes for variable 27. And variable 27 is the possible cause for variable 13. We see that the variable 3 is alone. It's not the cause or an effect for any other variables. We can also see that variables 29 and 26, I cannot come to a conclusion about the direction of the cause and effect relation here, okay? So I really like this procedure. It makes a lot of sense and works with the basic V structure we were working. But, well, say that normality of the residuals is not a hypothesis that makes sense for you. Well, I should not use this. You can have then the Lingan um, algorithm, the Lingan method. And we can see that it results in a very difficult graph, very different graph, okay? We have relations that, for example, the variable 3 now is related to other variables, and it's the possible cause of the variable 28. We do not know if it's a cause or effect of the variable 6 here. It is also the possible cause for variable 9 and whatnot, okay? But say that normality is okay. I can assume normality. What I cannot assume is the lack of confounders. Say that you see your field has a lot of possible common causes. There's a lot of possibilities. It's difficult to work with these hypotheses. Then you can use the FCI algorithm, because this algorithm produces causal hypothesis in the presence of confounders, okay? So we can see the graph is again different from the other two. It is more difficult to read because now we have those circles here. We have inverted arrows. We have double arrows, circles with arrows and whatnot. But this is a very complete model because, for example, variables 1 and 7 here, the double dotted edge means that we do not know if they have a common confounder. If 1 causes 7, if 7 causes 1, it's completely undetermined, okay? But if we look at, for example, the relation between variables 2 and 10, what the graph is saying here is that, well, maybe variables 2 and 10 have a common cause, or variable 2 is a cause for variable 10. It's not a possibility that variable 10 is a cause for variable 2. So you see that we are deriving some important implications here, right? Right? Even in the presence of a common cause, we can be sure, according to this method and the other assumptions it carries, that 10 is not the cause of 2. And there's even more impressive results, like the relation between the variable 22 and the variable 16 here, because it's a straight arrow, which means that variable from the correlation pattern we have, variable 22 is probably the cause of variable 16, and there's probably no common cause between them. So I don't want to go deeper in this. Just wanted to show you some examples so we understand that there are causal algorithms. They are interpreted in different ways. We have to know exactly how this algorithm or this method work, what type of assumptions the algorithm is making. But I hope it's clear that we have many methods, and probably for your data type, you have a method that you still don't know of, but you could use and start deriving some causal inferences from the correlational data. And like I showed here, of course, there are 30 variables, so there are many relations to look at and try to derive something relevant. But the tools, they exist, right? So the tools are there, out there. And if you look up closely, you will probably find them. And I hope you understand that, okay, I have a set of assumptions. And like most everything we do in science, the quality of our conclusions depend on the quality of our assumptions. Okay? So when we are talking about causality from correlational data, we have to be um, extra sure about what assumptions we are making, so we can start writing some inferences, some conclusions. Okay. So I want to summarize the takeaway messages here. And the first one would be that I prefer this version of the mantra, right? That correlation does not always imply causation. Sometimes, with the right set of assumptions, it does. And of course, the right set of assumptions and the good set of correlations and dependence patterns, right? I always wanted to leave this printed on your brain that non-significant correlations are just as or even more important than significant correlations. So if you are planning your study or if you're doing some assessment, don't go to the literature looking only for, well, what is significant and what I should add here that is significant. But also look for non-significant correlations. They are really important. They help us make a better picture of cause and effect types of relations. Okay? And use causal language without fear, but be aware of your assumptions. So this is a very common problem. Like you send out um, a manuscript for publication, you use say, oh, this variable calls this other one, and of course the reviewer will say, well, you're doing observational study, you cannot talk about cause and effect at all. But I hope I've planted a seed in your head to, well, actually, I can if my assumptions are correct. So I believe the best approach is make these assumptions crystal clear, and it shouldn't be a problem. Of course, there's always evil reviewer number two, and it doesn't matter what you write. There will always be some problem. Sometimes reviewer number three is even more evil. But I believe that if you make your assumptions and you explain, at least briefly, those ideas I presented here, you will probably be able to put your message out there. And everybody reading the paper would be, oh, okay, this type of relation, it's a cause and effect relation if those assumptions hold. And of course, this being explicit about your assumptions, it's again something important to anything we do in science, right? And remember, the world is complex. Always be aware of that. So you did a study with four variables. You calculated the correlation between those variables. You found a beautiful causal graph. But in your discussion, remember that you are limited by your assumptions. You are limited by the variables you measured. So you should play around like we are doing. Well, what would be other possible causes? What should future studies do to test the causal inference I'm doing here? Okay. So thank you very much for being here. I hope it was interesting, enjoyable, and that you could learn something from this. Ariella, I can hear you. I think you're.
Now I'm okay. Thank you, Vito, for your presentation. It was very enlightening. I think you definitely put some kind of seed for us to think about how much casuality we can think about it. I think we
Mhm.
have time for two or three questions before we finish. We start with a question that we received in the form. Okay. So one of the people, one of the individuals who signed up before for the webinar, they asked, "What's your view on quasi-experimental designs for causal claims?"
Okay. Yeah, this is a really nice question. And again, I think we have to think about what is the assumption we are making to derive a causal claim from a quasi-experimental design, right? So what is the characteristic of a quasi-experimental design? What's the difference from a quasi-experimental to an experimental design? Is the lack of random assignment, right? So a quasi-experimental design doesn't have the most important feature we talked about to come to a conclusion that you have a causal and effect type of relation. But again, like I told you, even some people do not agree 100% to what I said, just to be very clear. But yeah, you don't have random assignment. You cannot be sure you are avoiding the effects of confounders. But if you are explicit about this assumption and you understand what are the implications of the lack of random assignment, then you can even design a better quasi-experimental design, right? So you could think, well, a possible common cause here would be these variables. So maybe I should measure these and statistically control for it in my study. Or you could think of, well, maybe I have some network of variables here that would be important to understand the mediation between a possible independent variable and a possible effect, right? So again, is be sure about your assumptions and understand quasi-experimental studies are not using random assignment. Then you can work around and have a better design for your research.
Thank you, Vithor. The next question is from George. He asked, "How does this relate to path analysis?"
Cool. So path analysis is the implementation, right? Is you have the data, you have the theory, you go to your statistical program software of preference, and you run the analysis and you have the results, right? But the do calculus is what you do before putting your analysis, your data to the program. Is what you do when you are thinking about, well, what variables should I measure? What type of design should I do? What are the consequences of the causal claims of the theories I'm testing and whatnot? Okay. And path analysis is, okay, I have the data now. What should I do? And when you think about causal discovery algorithms, a way that I like to present them to my students here is to say they are basically like exploratory path analysis, you know? Because in path analysis, you have to say, oh, this is the exogenous variables, these are the endogenous variables, they relate to each other like this, and you say exactly what are the arrows. But when we do this, sometimes we are not thinking about the correlational implications from the causal structure, right? So, for example, the traditional mediation model that I showed you in the beginning, like A is a cause of B, B is a cause of C, and A is a cause of C also. The relation between A and B, it's not causally identifiable, meaning that from correlational data alone, you cannot come to a conclusion if A causes B or if B causes A. So if all the variables are correlated, you cannot be sure of this direction, right? So of course, you can implement the model in path analysis and do the fitting and all of that, and you will get to a conclusion and whatnot. But mathematically, that conclusion is probably incorrect. And of course, we are making theoretical assumptions, right? So again, for me, all comes back to assumptions. Be clear about your assumptions when you come to the part of collecting data and analyzing that data, right? But yeah, they are different like this. They are tools that serve different purposes, but from like causal discovery algorithms and path analysis, you can think they are kind of the same, but path analysis, confirmatory analysis, and causal discovery is like exploratory path analysis.
Thank you. One last question. And is longitudinal design always better than cross-sectional design?
Yeah, also that this is awesome, right? Because it's not uncommon to hear this from reviewers. If we are talking like from doing some mediation and whatnot, reviewers will usually say, well, but you should have done some longitudinal design so you can come to this conclusion and whatever, right? And my short answer for this is it depends. And of course, this is probably not the answer you wanted to hear, but again, what are your assumptions? What are you testing exactly? What types of consequences are derived from your theory and whatnot? Longitudinal design will give you way more information than a cross-sectional design, of course, right? But again, if we have the assumptions I told you before for using these structures to get to a causal inference, like the lack the lack of correlations are not effect of suppression. There's no common cause, hidden common cause, and we can say the correlations are correct and all of that. Then the conclusion you can get from cross-sectional design would be basically the same you would get from longitudinal design, because the mathematical property or the mathematical structure that allow us to come to this type of conclusion from a cross-sectional design should also be respected from a longitudinal design. Okay, but of course, like I say, like one assumption we do is there is no feedback loop, and you cannot study feedback loops in cross-sectional design. You need a longitudinal design to study this. There are actually also some causal discovery algorithms that do not assume that there is no feedback loop. Uh, yeah, the acronym is CCI for this type of causal discovery algorithm, if anyone is interested. It is based on a theoretical result showing that when you have a stable type of feedback loop, meaning that the relation is constant in time, then even in the presence of feedback loop, you can do some causal inference from cross-sectional data. Okay, so again, it depends on a series of assumptions. Longitudinal design overall is better because you have more information. But if you're talking about causal inference and conclusions we want to reach, again, what are your assumptions and do they make sense to your application or not?
Thank you. We have a follow-up comment of George Egelhard about your answer of a path analysis. He said he was thinking about the original conception of civil rights and not seeing related approaches.
Yeah, these are, of course, they come from different traditions, right? So the conception from right, I cannot say I am 100% familiar with it, of course, but I have read it at some point. Uh, and they are very close, right? Wright was also worried about assumptions and establishing them in a way that made sense. But again, they are in the level of implementation. And when we are talking about graphs, we are more abstract. So we are not talking about, for example, linear relations, or we are not talking about normal residuals or anything like that. We are talking about, well, if the conditional distribution of a variable depends on this other variable, we say this is a cause and effect. And what would change in the effect variable if we are doing changes to the causes? So the idea here is we are playing in the abstraction level, not in the implementation level. And basically, it's a tool for us to think, okay, if I'm doing a correlational study, and if my theory is talking about these types of cause and effects, what variables should I measure? And again, our theories are usually, oh, this variable is correlated with this. Our theories are most frequently not saying anything about, oh, this variable is not correlated to this variable, right? This is not common in psychological theory, at least From the theories I study, I rarely see this. So we have to think about that too. If we're going to correlational data, and if we at least want to try to make some type of causal inference from data, we have to think about the lack of correlations and how the lack of correlations or the lack of dependence of the underlying causal structure would impact the correlations I am observing. So this is what I was saying also with confirmatory and exploratory. I didn't mean like also the measurement part of the model, but I was talking of the structural part of the model also. So this, we usually say, right, we define the structural part of the model saying, oh, this latent variable is the cause of this, and the latent variable is cause of this. Or if we have the simple path analysis with no latent variable, we have to define, oh, this variable is exogenous, this variable is endogenous. But if we are doing, if we're applying causal discovery methods, we do not define this a priori. We get the correlations from the data, and from the assumptions for each causal discovery method, we derive some types of inferences. Okay, so I think this, I hope this made clear what I see the differences are.
Thank you, Vito. Once again, thank you to accept our invitation to this webinar. And before we finish, I would like to give you two reminders. By the end of November 27, we will have a webinar with Professor Matthias Ziegler from Humboldt University of Berlin. He will talk about response bias, faking. And also, a second reminder, we're going to have the ITC conference in Auckland, New Zealand, in 30 June to 3 July. And the call for symposium and individual abstracts was extended until December 14th. So we still have time to send your abstract to present at the conference. Be welcome. We will expect you. And of course, we expect you for the next webinar by the end of November with Professor Matthias Igles. Professor Vito, once again, really thank you for your presentation. It was very insightful. I think led us with many questions, and I think this is important. So you can go for and look for, have the curiosity about it, because it's something that we always afraid of to talk about causality in our cross-sectional studies. So I think you definitely have planted a seed on everyone who's watching. Thank you
Uh,
again. Thank you, everyone.
Thank you,
See
Adela.
you
Thank
next
you.
webinar.
Thanks for the ITC for the invitation, and I hope you enjoyed it. Bye bye.
Bye bye.